Hello, welcome everyone, live or online or later on. My name is Lieven and I am going to talk about coroutines. You could see it a bit as a back to the basic tracks on a feature which is like 4 years old, one of the big four of C++20. This is actually what we wanted from coroutines. We had a nice idea. Can we get it? This is what we got. So let's make the best out of this. A few myths. Coroutines are not related to multi-threaded and asynchronous programming. They can be used in that context, just like an integer value can be used in that context. Some people think if you talk coroutines, oh yeah, asynchronous. We will see in the examples today, I will try to keep them very trivial. We will not see any multi-threading. If we make it till the end, we will hint a bit on what we could do in a multi-threaded environment, but you can apply it there, but it's not fully a multi-threaded asynchronous feature. On that topic, I want to address very quickly concurrency versus parallelism. On the left-hand side, you see concurrency. You do a bit of that, and then you do a bit of another thing, and again, a bit of this and a bit of that. If it's parallel, both things are happening at the same time. It's not interleaved. You see, you have two cooks or you have two cores needed for that kind of purpose. Now, if we go back in time, the MS-DOS operating system, it could run one application, one process, and that was it. You couldn't do anything else. If you wanted to launch another application, you had to kill the first one. Then, when Windows came along, let's say Windows 95, you were able to, let's say, be doing some editing work in your Word editor, and you could also play Minesweeper. And you could switch between the two of them. And you had the impression that both were running at the same time. That was not true. That was the left-hand side, a bit of Minesweeper, a bit of Word. So two processes gave the impression to work at the same time. Now, processes are very big things. It's not fine-grained. Now, within a process, and let's assume there is still one CPU in our computer, within a process you can have several threads. You can have a thread which is doing some calculations, you have a thread which is refreshing the GUI, and again you have the impression that both are working at the same time. They are not. The operating system is preemptively switching threads. Suddenly the GUI thread is taken away and your calculation thread gets some slice of the CPU time. But it's already more fine-grained compared to processes. And coroutines are also something like that. It's even way more fine-grained than threads. Because switching from one thread to another thread is an expensive operation, because there is a context switch. Coroutines are way less fine-grained. There are other things like fibers, which are also for these kind of purposes. Okay, what's the difference between a regular function and a coroutine? They both can start and they both can end. Now, a coroutine has two extra features. It can suspend. It's not at the end of the function yet. Then it says, I'm going to pause for a minute. And later on, you can resume. You can resume where it left off. So a coroutine has two more features compared to a regular function. If you have a regular function and you call it, it starts at its first statement and it continues until its last statement and then it returns. With a coroutine, it's a bit different. When we are calling the coroutine, it starts, it's doing some stuff, and then it says, I'm going to suspend. And we return to the caller. And then the caller says, oh, I also have some work to do. It's my time now to do some work. And you know what? Hey, coroutine, time for you to continue a bit of your work, and so on. That's the flow. We never switch threads in what I was saying. The caller is on some thread, let's say in the main thread, let's say it's the main function, it's calling the coroutine, we're still in the same thread, we're returning to the main function, does some more stuff, it says resume the coroutine, So we didn't switch threads. No multi-threading here. When is a function a coroutine? It becomes a coroutine when in the body, one of the following three keywords appear: co-return, co-yield, and co-await. Later on, we will see what these mean and how you can use that. When the compiler spots these, one of these three keywords, it says, aha, this is a coroutine. I am going to do my special magic to make it behave like a coroutine, aka adding the two features of you can suspend and resume. And we're going to look at this from two different sides. We're going to look from the compiler side, because the compiler is going to do some magic, but the compiler needs help. And the help, unfortunately, needs to come from us. And we will also have the user-facing side. What does it mean using a coroutine? What's the user experience side of it? What's the UX? I can tell you now, we will see that the UX side is not that great. Doesn't mean it's extremely bad, but... So let's kick off with the first example. Let's model a radio station. When the radio station is created, it will have different types of music, and we will tell to that radio station, please, for me, play this kind of music, and please play for me this many songs. And out of that, a radio station will emerge, and it will play songs. Now, we're going to model that as a coroutine. So that means the coroutine is going to fetch, to prepare a song for us, and it will yield it back to us. We're going to listen to the song, and then we will say to the coroutine, to the radio station, please fetch, prepare the next song. So the disc jockey is there fetching the 7-inch or the 12-inch, putting it on the turntables, and then he says, I'm ready, I'm yielding back to you. We have a song database. It doesn't matter much. We have two types of music. We have rap music, we have electronic music, and we have some songs in there. They show my age, and they also show my favorite type of music. What if we would do that with a regular function? So we know we want to say the type of music we want. Don't do as I do. It should be an enumeration and not just an integer. We say how many songs we want. The function says, okay, I'm going to loop, and it's giving us the songs and as cououting. Now, we get all the songs at the same time, because this isn't stopping. This is going from start to finish. So what we would like is that, give me one song, that's it. Later on I say, please continue, give me the next song. So as a regular function, we cannot make this work. Pre-coroutines, we can make this work with a function object, and you call a function object, its function call operator multiple times, and you can make it work. We want to avoid writing this boilerplate ourselves. So coroutines, please do that for us. Now, when this coroutine is created, it needs to result in something. And in literature, you see different names for it. Some people call it the coroutine interface. Others call it the Coroutine API, the coroutine object, the coroutine remote control. Now, whatever we want to call it, I think it becomes clear it's not just a function, but it's an object, because we want to ask for the next song. We want to check if there are more songs, because I initially asked, please play for me 7 songs. So when all 7 are played, I should not ask for song number 8, because my credits are gone. And we want to stop at a given moment. I need to catch my train, and I'm not going to listen to song 5, 6, or 7. So we need to clean up. So it seems it's not a function, it's an object of some kind. So we already saw the music database. Those are globals, they are const, so we don't need to worry about that. But there is some state which is going to change over the life of the coroutine. It needs to remember what kind of music we selected, because that was a function call argument. the number of songs you want to play. The coroutine needs to remember that. And in the loop we saw, it needs to remember, is it iteration 1, 2, 3, 4, or 5? So the coroutine needs to keep track of some state. Now, when the coroutine is suspended, it cannot trash that state. It needs to keep hold of it, because when it's resumed, it needs to remember, you chose rap music, or we're at iteration number 4 now. So all this information needs to be stored and needs to be restored at the appropriate time. There are stackless and stack-full coroutines. I'm not going to explain the difference. The coroutines of C++20 are stackless. So this means this kind of information, the stack frame, is typically stored on the heap. Compilers can optimize according to several conditions. They are able to not put it on the heap, because that means no allocation needed. Now, let's go back to a regular function. What is a stack frame? When you call a function, several things are happening. I'm not going to be exhaustive, but a few things which are of interest is the caller is putting the return address on the stack. So when the called function, the callee returns, it knows where it needs to go to. Sometimes a placeholder is put on the stack for the return value, because if a function is going to return something, it needs to write that value somewhere so that it remains alive after the called function has returned. When you call a function and it has function call arguments, those arguments are put on the stack. And once you are inside the function, there can be local variables. Those are also on the stack. So we have put a lot of stuff on the stack when we call the function. When the function returns, all these things are removed. It is all cleaned up as if it was never there. Now, it's obvious a coroutine cannot do that. A coroutine, when it yields somewhere in the middle, it cannot say, I'm going to clean up everything, because otherwise all our information is lost. And that's why the stack frame is put on the heap. This also means the compiler, let's say the C++ coroutine ecosystem, is going to create a stack frame for us and put it somewhere on the heap. You all know if you allocate something, at a given moment you need to deallocate it. And now the question is, who is in charge for that? We, the developers, are typically in charge of that. So it's up to our responsibility to clean up the thing that was, the stack frame that was created on the heap, to clean it up at the appropriate time. Not too soon, because otherwise we would try to reference memory which is gone. Not too late, that's debatable, but don't forget, because otherwise we leak. So we have work to do. So when this stack frame is allocated, we get a handle to it, a pointer. That's our way towards, okay, over there in the memory, that's where all the state is being kept. And it's with this handle that we need to play and say, okay, handle, I am going to destroy you so everything gets cleaned up. Okay, let's go back to our radio station function, and now let's write it as a coroutine. There are two differences. We are now saying we're co-yielding. Co-yielding in this context means we're going to return already something. We're going to yield the value to the caller, and then we're going to pause. We're going to suspend. And while our regular function was returning void, we are now returning that object. Over here we said it's going to be an object of the type radio station. We have no clue how this object looks like at this moment. But this is writing the coroutine. So this is trivial code. If now everything would work out of the box, we would be very happy. It doesn't work out of the box. Now, this radio station object, when we look at it from the perspective of the user, it needs to be created. It's not the user who's going to create it, at least not in a direct way. We are going to create a coroutine, and that coroutine, as we saw before, or we're going to call the coroutine. So somewhere we will call radio station with its parameters, and then we will get the object. It needs to be destroyed at a given moment, so it's obvious this class needs a destructor. We need to be aware of, are we done? Is there still a next song to play? So we kind of need to be able to ask that class, are you done? So we want a done method. We want to say, can you now please provide me the next song? So we also need a method for that. Let's call it next. And when we are done, we should not call next anymore. And then you could argue about some other features. You could say this is scope creep, yes or no. When this radio station is created, should it immediately already give me a song? Or should it just put everything in place till I say, I'm ready now, I'm sitting down, now give me my first song. So it can start in an eager fashion, that means it's immediately already giving a song, or it can start in a lazy fashion. In our example, we will go for lazy. So this is one of the features of a coroutine. You could say, the moment you're created, off you go and start doing work, or the moment you're created, sit ready, I will come back to you and say when we really start our business. Next and done, in our class of radio station, let's combine it and call it next song. If it returns true, it means it has prepared a new song for us. If it returns false, it means it's done. You asked for n songs and you got all of them. We're done. The next song, you could call this the resumption method. So it will only signal us if there was something more. We didn't get our song yet. We were just told, yeah, it's ready for you. You can come and pick it up. So we need to explicitly fetch our song. So we will need a method to really fetch our song. So from the user's perspective, when we look at main, it kind of looks like this. We create a radio station. 0 means we want rap music and we want 7 songs. So we're calling our coroutine, which returns the Coroutine API, the Coroutine interface, our radio station. We say, try to give me the next song. aka we are resuming the coroutine. When that says, yes, I was able to do something for you, then we say, okay, let's fetch the song. I wasn't very inspiring on name, so I chose, let's call it value. And that's using it. So we saw the coroutine itself. It was rather trivial, and I think this is also trivial code. So trivial, yay, that's easy. Well, still our homework is not done yet. Now, let's have a look how the compiler looks at this. So the compiler knows this is a coroutine and you're telling me to yield something. That means the compiler needs to be able to store that value somewhere, because it's not the return value of a function. It's in the middle of a function. So the compiler says, I want to be able to store it somewhere. And then you, user, later on, you can fetch it from there. Okay, fair enough. We already saw that we can say, are we going to start eagerly or in a lazy fashion? Compiler needs to know that. So compiler is going to ask us the question, eager or lazy? That for him, it's answering the question, should I suspend at startup, yes or no? Symmetry is nice. So you can also configure a similar thing at the end of the coroutine. So when the coroutine is about to be ready and return, you could say, should I do a final suspension at the end? Or do you want me to exit or finish immediately? Another thing that the compiler wants to know, what if an exception occurs? What should I do? If an exception escapes, let's put it like that. So you don't have a try-catch block. What should I do? The compiler wants help from us. And the compiler is also going to create that return object, that radio station class instance. Compiler doesn't know how it should be constructed, because maybe it needs a constructor argument. Compiler cannot guess that. So again, compiler is reaching out to us. Can you help me on that matter? All this, let's say, configuration of the coroutine is done in what's called the promise type. It has nothing to do with std promise. It's a concept. It's a promise type concept. It's just a little struct which adheres to the promise type concept, and we as developers need to implement that. The promise type concept is going to require that several methods will be implemented, but you don't always need to implement all of them. It depends on what you are doing. One of the methods on the promise type that we need to implement is, should we suspend at startup, yes or no? This is a signature of the function. Let's ignore the return value for now, what its type is. Initial suspend, and we say suspend always. So that means when the coroutine was created, it's immediately going to suspend. That's the lazy start. Or we say suspend never. Coroutine is immediately already working and is immediately going to return a song to us. We could do this configuration at start, but also at end, the final suspend. Either we say suspend always, so the coroutine is actually ready, but we say, yeah, at the very end, suspend one more time. Or we say, no need to suspend at the very end, just finishing up, clean up, and we're done with it. It wants to know, what should I do if there is an unhandled exception? So an exception occurred, nobody is catching it, so it's going to get out. For that purpose, it wants you to implement a method called the unhandled exception. And there you can do whatever you want. The most easy implementation is say, let's fail hard and let's fail quickly, so we just call std terminate in our example. So what do we know already of the promise type at this moment? Initial suspend, yes, always suspend at startup. Final suspend, yes, always suspend at the end. And in case there is an unhandled exception, you know what? Stop the entire thing. That's what we know for now in the promise type. We need to implement this. We have to. That's the IKEA work. Now, when the coroutine generates values, as our example is doing, and suddenly there is a song ready for us, it needs to be able to store that. It wants to store this in the promise type. Until now, there was no state in our promise type. There is not a single member. It are just functions with implementation which don't require any members. Of course, if it now wants to store the value it's going to yield, we need state in our promise type. So our promise type is going to need to have a member, and the compiler says, when you want me to yield the value in the promise type, you have to provide a method which is called yield value, takes an argument of the type that I am yielding, and it returns something. Again, let's ignore what kind of type this is. let's have a look at an implementation. So we add a string member to our promise type. So our promise type now has state. On yield value, the compiler is going to pass in the song it has created for us. We say, okay, let's store it in the member. And yeah, we were yielding. We were on the way to suspend. So suspend always. We've already seen suspend always in final suspend and suspend at the beginning. And now also during co-yielding. So our promise type got a little bit bigger. We have an extra method. There's still no difficult rocket science in here, so it's annoying. We need to do this. Now there is one thing still missing, and then we can have the stuff working. As the compiler wants to create that radio station object. And in order to do that, it wants in the promise type a function to be implemented called getReturnObject. So this is what we are still missing. We will come back to this a little bit later. Now, let's recap. There is a promise type where we kind of add configuration stuff for the compiler to deal with the coroutine. We know there is a stack frame and we have a handle to it. The promise type is stored in the handle. That's also interesting to know. So you have kind of like the stack frame with all the local variables and etc. And there is also that promise type. And both together, they are in that handle. The return object, our class radio station, is going to get that handle at constructor time. That's the compiler coroutine ecosystem that says these are the rules of the game. So our class radio station is not going to create that handle. No, it's going to get the handle when its constructor is called. And then our radio station is going to own, typically it will own that handle and it will destroy it at the appropriate time. And we already identified that our radio station class should have a destructor, so that's most probably the appropriate place to destroy that handle. The handle itself contains the promise type, and for that purpose, it's templatized on the promise type. And the handle, that's really from the compiler perspective. So the compiler says, yeah, but a coroutine, I need to be able to resume it. So the handle has a method to resume. Makes sense. It has a method to check, are you done? Makes sense. It has a method to destroy it, so we don't leak. It provides a method to check, is there a handle? There can be use cases that the handle is already gone for some reason. And we have seen that the promise type lives inside the handle. So if you have a handle, it would be nice, you could get hold of this promise. For that purpose, it provides also a promise method. All seems to make sense. Now, we know that our radio station is going to get the handle at constructor time and is going to own it, so we store it. So we say we have a subtype called the promise type. It needs to be that name, because that's what the compiler demands. And we say, okay, let's give a name to a coroutine handle templatized on this specific type, promise type, and we call it coro handle, and that's our member, which comes in at constructor time. We store it. At destructor, let's check if there is still a handle. Maybe for some reason that's no longer the case. If it is, we're going to destroy it. And there is probably much more to do in our radio station class. Okay. In the beginning, from the user's perspective, we identified we are going to want in this API a next song method. We know that our class has a handle. First thing, is there a handle? If not, we're done. We return false. There is nothing more to do. If there is a handle And when we ask the handle, are you done? And it says yes, again, we're done. There's nothing else to do, no more songs. Otherwise, we say to the handle, resume. So from the user perspective, next song, we could have called it resume, is basically just forwarding to the handle, hey, handle, can you resume? And at the end, we return, are we done or not? Because maybe this was now the last, let's say, resumption that could not even lead to a value because it ends up at, let's say, the closing curly brace of the coroutine. And if we suspend there, a final suspend, it's like, okay, we don't have anything. We're just at the end of the coroutine function. We're not going to co-yield anymore. This is another way to write it. So we've already seen this before. Our next song, which implements are you done? And if not, is there still something more? It returns true if there is something more and false if there is nothing left to do. We need to get that value, the song. So next song says, yep, return true. I have prepared the song for you. We still need to fetch it with the interesting name we gave to the method value. So how do we get that? Our radio station had a handle, which we got at constructor time. We've seen that the handle allows you to get into the promise by calling its promise member. And in the promise, we had created a variable to keep track of a state, and we called that member value, where the yield value function of the promise type called by the compiler was storing the value. So compiler co-yield, oh great, promise type, yield value says, oh great, I will store it in my value member. And then from the user side, it was like, okay, next song said there was something, okay, let's call value, and this one says, in the handle, give me the promise, and I'll give you the value. Compiler put something in, we were able to get something out. Great. Back to that getReturn object. That's the one thing which is still missing to have working coroutine. So the getReturn object is called by the compiler to create the return object, an instance of this radio station class, which we know it needs to accept at constructor time the coroutine handle, and maybe if there are other arguments, they should also come in. In our case, there are no other constructor arguments. So the first thing that happens, the promise type is created because the promise type lives in the handle. So step 2, we create the coroutine handle. And then step 3, we call our radio station constructor, which gets the handle as its constructor argument. And then our object is created and we can return it. Step 1 and 2 can be combined because the handle has a factory method from promise. So when I am in my promise type, getReturn object, that's a method of the promise type, I can say Coro handle, that is an alias for this part, from promise type me, this. This gives us the handle or creates the handle, and then we say, okay, let's return an instance of radio station which has one constructor argument, that handle we just created, and we saw radio station and says, this is mine, I will own it, and at destructor time, I will destroy it. We can put everything together. So this is our radio station class. Constructor, destructor, we saw it before. Next song, if there is still something to do, we resume, we return if there was actually something delivered. If so, later on we can say, give me that song. So that's our radio station class, which has a subtype promise type. So how does the entire promise type look like? Initial suspend, final suspend, unhandled exception, getReturn object, and yield value. I have also put here return void. I'm going to ignore it for now. I will come back in another example. In theory, it has to be there. That's what literature says. I tried it out on GCC, and if it's not there, compiler's happy. So most probably that's a bug, or I didn't find the fine print that said that maybe it's not needed. So putting it all together, this is actually what we want to write. On the main using the coroutine and the implementation of the coroutine. But of course we have seen there is this, the promise type, and there is also this. So there are a few things we need to know how it works, and we need to implement it for every coroutine we want to create. Quick pop quiz. I want my MTV. Who sang that line? In which song of which group? Dire Straits is correct. Which song? Money for Nothing is correct. And who sang that line? Sting. Yes, well corrected. Good. This again shows my age. So I want my MTV, well, I want my iterator, because a while loop, ooh, that's old style. We want range base for loops. Range base for loops want an iterator. We don't have an iterator, so let's go and provide one so that it looks like this in the end. That's nice. There is no more next song method. There is also no value method. It already looks a bit nicer. So, an iterator. For the range base for loop to work, it needs to be able to call on the type, aka radio station, a begin method, and an end method. An iterator, in our example, needs to be able to be incremented, go to the next item, and it should be able to be dereferenced to get the value the iterator is pointing to. The iterator should be able to be compared. Are we equal to the end or not? So, all stuff we need. Incrementing the iterator in the light of the coroutine actually means resume, aka next song. And dereferencing the iterator was our old value method. So we need an extra type. The iterator type will live or implemented in the radio station. This is very obvious. And we already feel we are going to need the handle, the coroutine handle, because if we want to increment, yeah, we said that that's equals to resume, so we know on the handle you can call resume. So the iterator will need the handle. Now say that the iterator is at the end because the coroutine has finished. Maybe it could be an interesting idea then in the iterator to put the handle to the null pointer. So the end iterator could be our iterator class with the handle pointer null. And as long as it's not the end iterator, the handle pointer is not null. So increment means handle resume. Again, that's not that hard. Iterator, it gets that constructor time, the handle, it stores it. Dereferencing, that's handle, give me your promise, dot value. That's basically the same implementation as our value method we have written before on the radio station. Incrementing the operator, let's first see if there's still a handle. If it is, handle resume. In case it's now done, it means there is nothing more to give. We will say the handle is a null pointer. Our iterator is now at the end. And the iterator should be comparable. C++20 feature, a spaceship operator, but now only for equality. Default is okay. Default means we will compare member by member. What is our member? It's the handle, which is a pointer. So comparing two pointers means yep. And actually we are going to compare pointer versus a null pointer. Oh, again, this is not so hard is Iterator, but we have to write it. And the radio station needs two extra methods. Begin. If there would be no handle anymore, or it was done, we create an iterator with a null pointer. The end iterator is the same thing. So begin could also be a null pointer because there is nothing there. Like there was, if you would have an empty container, begin would also equal end. If there is something, we create an iterator based on this handle, and we already increment. We already resume, so that begin actually points to a value. And then the range-based for loop will work. So, what can we conclude until this very moment? I started at 11:30, yeah? Right, okay, so I can go to 1 o'clock. The coroutine function itself, it's not hard. The code in main also looks easy. All those boilerplate concepts, they are also not that hard, but it's annoying that we should deal with it. And now there is a question that you can think about, you can answer for yourself. Is this production ready? We are all experts now, so we understand it. Will your colleagues understand it when they see this code? Or is it, as Kevlin says, we have wrote some code, we're 5 minutes later and it already becomes legacy code? Because your colleagues, they don't know what is this. Ooh, promise type, what is this? I'm not touching that. Code we are afraid to touch, legacy code. So, now, if we would just have the following and be done with it. So we have, I think, if we put all the slides together with code, which we have seen, I think we had, I don't know, 8, 9 slides. What if we could replace it by this one slide? We can. C++23 brings a stud generator, because our radio station is nothing more as a generator of songs, where songs are just song titles, strings. So it was a generator of strings. So we say std generator of strings. Let's call this a radio station. This is the same as before. This didn't change anything, but all the boilerplate was replaced by a one-liner. And we also get the iterator. We get it all. Now this is interesting. C++23, not in C++20. GCC 14, which is coming shortly, has this. Clang 18, which was released 1 month ago, doesn't have it yet. And on Visual Studio, I have no clue. Okay. A second example. We're going to create a pinball machine. All my examples are really stupid. Imagination. Remember what we learned earlier this week? So this again shows my age. When I was a student, this pinball game, the Addams Family, was very popular. You can find them online if you're a rich man, because they cost a lot of money. Okay. So we're going to have a coroutine that on each resumption is doing stuff, playing the pinball machine, but it's not returning anything. So not co-yielding. It's doing stuff, and then it says, oh, okay, I'm pausing for now. I need to take a break. And by the way, there is nothing I can give you. This will be done by the keyword co-await. And as with the generator example we saw before, and this, it could be that the coroutine never stops. A typical example of the generator is the Fibonacci sequence. Well, it never stops. So there are 2 players. I am player number 1, and the coroutine is the other player. And each we take turns. So collaboration, remember the fine-grained collaboration? Now it's up to you to use a CPU a little bit or the pinball machine, and then it's up to me. We want to win, obviously, so we're going to make the coroutine lose, and the coroutine will get n turns to play the pinball machine. The resume method, next song, now let's give it a call. Let's call it play. It's not going to give us anything back, so there is no need for a value method to fetch something. That's great, less work. And the end turns, how many times a coroutine is allowed to play, that's the, let's say, the function call argument of the coroutine. Before we had two, the type of music and how many songs. So the pinball coroutine loops, says I am playing, and then says, instead of co-yield, it says co-await, suspend always. Remember before we said co-yield, title of the song, which went into the promise type yield value, which stored the value in the promise type, and then also said return suspend always. So it looks a bit similar, but different keyword and no value to return. In main, instead of radio station next song, we decided now to call it play, pinball play, now I am playing, and so on. Coroutine is easy, using it, it's again easy. Boilerplate time. There is no need to store anything, so we don't need to implement yield value, yay. We don't need the member to store anything, so we can kick the member out from our previous example, but we need to implement another function, which in the previous one we also, in theory, had to do, and that's return void. The compiler wants to know, what do you want me to do, or how do you want to configure if I'm at the end and I want to return nothing to you? Return void. In our example, I have no clue what interesting stuff we could do, so we will implement it empty. So the promise type of our pinball get return object, that's the same recipe as before, only it's not radio station but pinball. At startup, yes, suspend. At the end, yes, suspend. If an exception would escape, you know what, blow up. And at the moment you're ready to return nothing to me, I'm fine with that, I'm not going to do anything. The pinball class, as before, it has its promise type. There is the handle, it gets it at constructor time, at destructor if it's there, destroy it. The play method, next song, see if we should resume, otherwise we're done. And when we resume, we also return the outcome. Are we now done, or did we just still do something? We're done. So we already gained some knowledge from the radio station. We reapplied it, but we had to reapply it. We had, again, to write all this boilerplate. Now, cheat the system. Stud generator wants to return something. I tried, stud generator of void, would that work? Nah, bummer, doesn't work. Okay, let's return an int, and don't forget the comment on your class that nobody reads or which lies. Don't do anything with the value I give you. So not co-await, co-await suspend always, no, co-yield of 0. So it's going to return on each resumption an integer value of 0. I couldn't care less. And then it's going to suspend. Okay, this works. Each time I get the value, I couldn't care less, but I've implemented it with stud generator in the end. Is this a hack? Is this a smart idea? It's up to you to decide. It's just something which co-awaits. In this example, you can also implement it with stud generator. You're going to yield something where nobody is interested in, but you can avoid the boilerplate. Let's try a third example. Now, suppose we have a coroutine that each time is going to do some work, then pause. When it's resumed, it's continuing to do some work, pause again, and after all resumes have been carried out, it can go till the end of the coroutine, and at that moment, it's going to return us a value. For that purpose, we need two keywords, co-await, the one we saw in the pinball. We do something and then we say, I'm suspending and I have nothing to tell you. But then at the end, I do have something for you. So we're going to calculate the average of a very large set of values. So on every resumption, we could already add some of the values. On the next resumption, we add some more values. And at a given moment, we have been resumed enough so that all values have been added. And we can divide by the number of elements. And we have calculated the average and we can return it. Again, a very stupid example, but it can be modeled with a coroutine. From the user's perspective, so radio station pinball, we will now call the class average. There is again the resume method we need from the user perspective to say, yep, please continue. Let's call it calculate in this example. And this time, again, we need to be able to fetch the calculated value, not on every suspension, but at the very end, when everything is done. How does average look like as a coroutine? So the big set of numbers, they come in as a vector. We loop over them. We're number crunching the next value. We add it to the sum and we say co-await, suspend always. I am going to resume. And by the way, I have nothing to tell you. After a while, we have looped, resumed and looped enough. We say, finally, everything is calculated. And the coroutine says, now I'm going to co-return the calculated value. And after this statement, you have the final suspend thingy. On the user side, the code also looks very trivial. As long as we are calculating, and there are more calculations needed, at a given moment, the coroutine says, everything is done. So we fall out of the while loop, and we say, OK, we need the result. So again, on our return object, Coroutine API, Coroutine interface, whatever you want to call it, we will need the method getResult. Just like we had on the radio station, give me the song value. Here we already have a better name. So we have improvement in naming. So in the promise type, in this scenario, again, we need to store, or the compiler is going to store, the end value. In order for the compiler to be able to do that, it doesn't need yield value, because we're not yielding. It's also not return void, because this time we are returning something. It wants a method to be implemented in the promise type called return value. And the promise type, once again, needs a member, needs state, so that this value that comes in can be stored in the promise type, and later on, we can retrieve it. So this is our promise type, all as before, but now we have the method return value, where our integer is coming in, we store it, and we have the number. So the compiler is already able to store it in our promise type. So all what is missing is, so this is as before, the average class. And all we still need to do is add the getResult function, which says, handle, give me your promise. And we know that the member in there was called value. OK. We're done. Cheat the system. Can we do this with stud generator? Yes, we can. A stud generator of an optional of int. On each yield, we return an empty optional. So we can check, or we can loop, are we done yet? Or we check, oh, the optional is empty, so we're not done yet. And at the end, we co-yield again, so not co-return. Let's use co-yield once more, but now the optional is not empty. So we're having the loop. We could do this. We need to do it in the loop, because we're looping all the time, empty optional, empty optional, empty optional, empty optional. And for this loop then, a non-empty optional. And then we know we're done. Yay. And it would be a bug if suddenly you could do an extra iteration. But who will give you the guarantee? Huh? So, is this interesting? I'm just showing also this example. We could already hack it away with stud generator in C++23. All right, awaitables. We are cranking up the complexity on coroutine with a little notch. So we have seen the promise type, which allows us to configure a bit the coroutine so that the compiler knows what to do. Should I suspend at the start or at the end? It was, let's say, our secret locker for the coroutine to pass in a value and for us to retrieve the value. Great. But there is another configuration point, and that's called an awaitable. What are awaitables? Awaitables are the operand of co-await. Remember, we wrote co-await and then something. That something is an awaitable. It's also used in case of co-yield. Remember, in our implementation of yield value in the promise type of radio station, we were storing the value and then we were also returning suspend always. And awaiters are a specific way to implement an awaitable. We will see some examples. So whenever co-await and co-yield is called, actually awaitables, awaiters come into play. So that means we already know two awaiters. We will see them shortly. Now, an awaiter, it's like the promise type. It's a concept. It needs to have three methods: await ready, await suspend, and await resume. Could this be interesting? The first one, await ready, is called by the compiler, by the C++ coroutine ecosystem, the moment before the coroutine is suspended. So it's not suspended yet, it's about to suspend. And just before this is happening, await ready is called. This allows us to do stuff just before the suspension. Interesting stuff, maybe non-interesting stuff. And it needs to return a Boolean value. If it returns true, true in the sense of ready, yes, true. That means it's ready, ready. Then I should not suspend. So we can say, no, we're not going to suspend. If we return false, it's not ready, then we say, suspension is a good idea, let's do it. A use case could be the suspension depends on if data is available or not. Await suspend. Await suspend is called immediately after the coroutine is suspended. Control has not reached back the caller. So we're not, in our radio station example, we're not yet back in main, but the coroutine is suspended. And await suspend gets the handle of the coroutine that has just been suspended. Again, we could neutralize the suspension and say, well, I've changed my mind. And await resume. Await resume is called when a suspended coroutine is resumed. When a suspended coroutine. So that means if in await suspend or in await ready you would change your mind, it's not suspended, so await resume will not come into play. And await resume can return a value. And the value that await resume returns, that's the value you get from your co-yield or your co-await expression. So we saw in the radio station co-yield and then some string. This returns a value. So we could say auto foo equals co-yield our string value. So as I said, there are already two awaiters we know of, suspend always and suspend never. Their await resume and await suspend are empty. They don't do anything, but they are different in the await ready. Suspend always says await ready, false. Means it's not ready, means suspension is going to happen. Suspend never says await ready, true. It is ready, so we're not going to suspend. Applications of these awaitables. Coroutines calling coroutines. Let's see if we get there. We have 30 minutes left. But another application is passing values back from the caller to the coroutine. So when the coroutine yields us a value at the suspension time, we get it as a caller, we get that value. But what if we would like the next resumption to be influenced by something we want to give the coroutine now? It's like, okay, you got me something. Could you please resume? But wait a minute, I have something for you. I have something for you. Use this. Let's do that on our radio station. When we get a song and we will ask for the next song, we're going to give feedback to the DJ. We're going to say, we appreciated that song, or come on, this is awful music. Pre-2000, post-2000 maybe, I don't know. So passing values between the coroutine compiler and the caller, we know what we need to use, the promise type. That's the thing where we exchange information. So that means our promise type will need a new member where I, as the caller, I'm going to store a value, and then the coroutine, the compiler, is going to fetch the value that I stored in there, and it will pop up in the coroutine as the return value from the co-yield expression in the coroutine of our radio station. So how does the coroutine get it out of the promise type? I think it's very trivial for us from the caller side to stuff something in the promise type. But how does the coroutine will get it out? And that is going to be done by an awaiter. But none of the two awaiters we know of, because they are too trivial for this purpose. So it's back to us to come up with a solution. And let's inspect these one by one. So on our API, our radio station class, we need a method to pass our value in. Let's call this value, or this method, score, radio station score. We provide our appreciation of the song, and in the promise we store it. So the promise type will need a member called score. And how will we call this? At, let's say, a pimped API of the radio station. As before, is there a next song? Okay, give it to me, I'm listening to it. Oh, I like it. 10 out of 10. Resume, please. Give me the next song. We like them all, so we're each time giving a 10. Oh. Small change from the user perspective. All right. The promise type, we said we're going to store it, so it now has an extra member. So its state got a little bit bigger, score, and the yield value that we implemented at the beginning, the one which would store, let's say, the created song into value and then says suspend always, that one needs to be changed. Now let's go to the coroutine first. So we know that the co-yield can return a value. That's the score. Okay, the previous track scored, we used it. So from the main method, let's say from the user side, it was easy to say, hey, radio station dot score, you get a 10. And in the coroutine, it's again very easy to use it. We need to solve it in the boilerplate. So we used to return in the yield value, we used to return suspend always. Now we are going to return an instance of our custom awaiter. Let's call it my awaiter, and it's templatized on the coroutine handle. Later on, it will become apparent why. That's all we need to do to change yield value. Of course, we still need to implement it awaiter. Now, how should we implement this? Await resume can return a value, the value of the co-await expression, or the co-. So that's what we said. In our case, that means that await resume on our custom awaiter should return that score. That score, which from main we stuffed into the promise type. The promise type, which lives in the coroutine handle. So if our awaiter would have as state the handle of the coroutine, the problem is solved. Let's assume that magically the handle got into our awaiter class. Then we can say, so our awaiter class has a member called handle. Let's initialize it at null pointer. That's not that useful at this moment. Await ready, return false as before. We want to suspend. There is one method still missing. We'll come back to it. Await resume. Okay, handle, give me your promise and give me the score, the thing that is in your state. So if that handle would end up in there, we can solve the problem. Good, one step closer to the solution. Now, how do we get this handle in there? Well, remember, await suspend receives as the argument, because that was the only method which has a function called argument, the handle of the coroutine that just has been suspended. So the coroutine which has just been suspended, when await suspend is called, that's the handle we get. Well, let's store it. Let's store it in our awaiter class. We have a little bit of state, one member, the handle. So we got it in. And then await resume can use it. So this is our awaiter. It has one piece of state, the handle, which is initially the null pointer when it was created. Await ready. And so co-yield something. Compiler says, okay, let me first double check. Are you sure you want to suspend? Yep, we are damn sure. So ready, no, return false. Then just after the coroutine has been suspended, the compiler calls await suspend with the handle of the coroutine which was just suspended. Thank you very much. I will keep track of this. I will store it. Later on, somebody says, hey, coroutine, please resume. And they have filled in the score. So the score is in the promise type. Okay, await resume says, I have a handle. Hey, guy, give me your promise. And in there, give me the score. And that's what's being returned. And the return value of await resume, that was the value that co-yield will return. And we have the value in our coroutine. So we were able, before we resume, to say, hey, and I have some information for you I would like you to use in a useful way or in a stupid way like in our example. It's a PDF, so it doesn't move, but this again shows my age. Hannibal and face. Okay, let's see where we are. Alrighty. another use case of Awaitables was when a coroutine would call another coroutine. And you can think of examples. We have met the concept of lazy evaluation. Coroutine doesn't kick off immediately. Now, let's say we want to write a parser. There are a few ways you can go about it. You read in the entire file, then you lex it, so you have tokens, the entire file, and then you do the consumption of the tokens to parse to see that already on the first line somebody forgot the semicolon, and you say, syntax error. Another way could be, suppose that all three are coroutines. The parser coroutine says, hey, lexer, can you give me something? The lexer goes, it's lazy. Before it can continue, it says, hey, file IO, can you give me some characters? This coroutine says, yeah, here's something for you, and I'm going to suspend now. Lexer says, this is not enough information. Could you please resume? I want more input data. And there is more input data. The lexer at the given moment says, yes, I can create a token out of it. Parser, back to you. I'm going to suspend. The parser says, great, one token. I need more. Lexer, can you please resume? And so on and so on. Everything is done in a lazy way. So we didn't have to read in an entire files and waste a lot of memory, lex everything. Assume this takes a lot of time, and then to see that already on line 1, everything is wrong. So we're not going to look at the return object here in much detail. We're going to talk about it. Let's say that the outer coroutine, which calls the inner coroutine, are of the same type. We could call coroinner. This is not going to work, because what happens, this returns the coroutine object, the Coroutine API, and we don't store it. So it gets constructed, and at the same line, it gets destructed. So nobody is resuming it. No, that doesn't work. Because, yeah, I forgot to mention, our goal is that the resumption points of the inner coroutine should kind of act like resumption points of the calling coroutine. As a calling coroutine, I'm calling an inner coroutine, and next to that, I also have my own suspension points. But to my user, it should look like there are a bunch of suspension points, and I have no idea if it were yours or your inner coroutine. So another solution is we explicitly loop. But we're looping, we're not suspending here. There is a suspension of the inner, but we ourselves are not suspending. So this is also not the correct solution. Awaitables can help us solve the problem. We're cranking up the complexity notch again a little bit. Now, what if that API, the coroutine object, would be an awaitable? It means it needs to implement the 3 methods of the awaitable concept. And that can help us out. Because we're going to work with that idea, but there is also the other thing we should reflect upon. Remember, all our return objects, they had a resume method. Next song, calculate, play. And they are checking a handle, and then they resume it. Who says we need to resume the handle of the outer coroutine? We could as well resume the handle of the inner coroutine. And as long as the inner coroutine is not finished, let's just resume the handle of the inner coroutine. When that is finished, let's continue resuming our handle, aka we are the outer coroutine. Now, let's assume that the handle of the inner coroutine magically appears in the promise type of the outer coroutine. And so that means we're going to store it in the promise type of the outer coroutine, and let's give it a name, msub. So let's assume we can get it there. One problem at a time. Then resume could look like this. So resume on the outer coroutine. If there is no handle or we're done, Get out. What's the handle we're going to resume? Well, the handle of the outer coroutine. Let's ignore these lines for a moment. Handle resume, and we're done, or we're not done. And now we have this extra thing. Well, is there a while loop? I want to allow this to have multiple chains. So I am the outer coroutine. Do I have a sub handle? If not, it means I'm not calling an inner coroutine, so we don't bother. If yes, and that inner coroutine is not done yet, that should be the handle we want to resume. Handle is no longer the handle of the outer coroutine, it's now the handle of the inner coroutine. Because we assumed in a magical way that we know it. And we still need to solve that. How do we know it? But assume that this problem would be solved, we can say, okay, that's the handle to resume. So that means somebody calls us and says, hey, outer coroutine, you should resume. We come to the conclusion, yeah, but we have an inner coroutine, we have an msub handle, and we see that that one hasn't finished yet, so that's the one we resume. So how do we get that sub handle in the promise type of the outer coroutine? We have said that the inner coroutine is an awaitable. And so it implements the three methods: await ready, await suspend, await resume. Now, when we see co-await of the inner coroutine, which is an awaitable, this means that on the, let's say, the return object of the inner coroutine, the method await suspend will be called with the handle of the coroutine which is being suspended, which is the outer coroutine. So suddenly, we're calling in the return object of the inner coroutine a method await suspend, and this is the handle of the outer coroutine. So suddenly the inner coroutine knows the handle of the outer coroutine. Oh, great. Handle of outer coroutine, can I get your promise? Yes, sure, here it is. Your member msub, hey, that's me. So the inner coroutine gets to know the handle of the outer coroutine and then decides, I am going to store my handle in you. So we were able to get it in. Await suspend. So the handle of the outer coroutine, because that's the one which is suspending, promise type msub, hey, that's me. Because the inner coroutine object, as all our radio station, Pinball, they all had a member mhandle. So one coroutine can call other coroutines, and to the user it all looks like many suspension points. And he has no clue, is it now the inner or the outer? It's like, okay, we need to wait. The big thing is suspending. I love it when a plan comes together. You could say, yeah, that inner coroutine needs to be an awaitable. I think this is a bit intrusive. I had my nice little class, and now you enforce me to write 3 methods on it. Await ready, await resume, await suspend. There are a few other ways. Any type, foo, or maybe an integer value, could be returned for a co-await. We know that co-await in the end should return an awaiter. Now, foo is not an awaiter. An integer value is also not an awaiter. So what are, let's say, plan B and plan C in this case? If the promise type has a method called await transform, taking an argument of the type that co-await is returning, it can be converted into an awaiter. In a promise type, you need to implement await transform. So there you will implement your customer awaiter or whatsoever, but it's within the promise type. You're not polluting, let's say, your radio station class, your pinball class. It's a matter of what you prefer. Or your foo class does not provide the three methods. It only provides one method, the operator co-await, which then again returns an awaiter, which has the three methods. It's a bit less intrusive. It's a matter of style. What do you prefer? Which one fits best in your design? Now, await suspend, that's the one which is called just after the coroutine has been suspended and gets the handle of the coroutine which has just been suspended. It can have three different return types. You can implement it with a return type. I cannot see it because of the light. 10, thank you very much. It can have a return type void. It can have a return type bool, or its return type could be a coroutine handle. So when the return type is void, actually we can do some extra stuff, but suspension remains in place. That's all we can do. We've seen the examples. We just stored the handle because we were going to use it in await resume, and we return void. It could be we return a Boolean value. We can again do stuff, and then we say return true. Go ahead with the suspension. Or don't go ahead because it has been suspended. Don't invert the suspension. And when we return false, it's the other way around. Yep. We say, I changed my mind. Don't suspend. You just suspended, but I changed my mind. Don't go back to the caller, immediately go back into the coroutine. Or when it returns a coroutine handle, might be a coroutine handle from a completely different coroutine, then we are actually saying we are moving on with the suspension, okay? But we are not going to return to our caller. You know what? Immediately resume the coroutine of the handle I give you. And that's called symmetric transfer. You could end up with this in an endless loop. Because at the given moment you say, yeah, but now it is time to return to the caller. Yeah, but we are returning handles, so we're going to resume the handle you return. There is a special no-op coroutine handle, which means here it ends. We're not going to call or resume another handle. We're going to return to the caller. And I'm dropping a word here, continuation. When could this be interesting? Final suspend. In all our example, final suspend was suspend always. Now, if you have a coroutine which is completely done, you could say, well, then continue with this coroutine. So don't go back to the caller. No. Coroutine X, you're done. And magically you know of the handle that you should continue with that other handle. So we're not going to the caller and then the caller needs to kick off the other or resume the other. No, we directly do it. We're gaining CPU cycles. So other ideas of continuation. We were already promised for a very long time an extension to stud future that you could say, thank you very much, dot then on a future. That's also a form of continuation. Completion handlers in Boost ASIO, it's also continuation. Oh, here you see we're getting very slowly into the asynchronous world. Do something and then continue with this. We're not going to go into detail for that. Final suspend, yeah, I mentioned that, which is great because there are 5 minutes left, so we have 5 minutes for questions. Thank you very much.